Okay, so we want to talk about the frequency response of op amps. So you can see here is a op amp. So I just grabbed the LT010, the 1001 op amp, and so we have to give it the two supplies, and then we're not looking at it with feedback. So we're looking at it in the what's called open loop configuration. So we're going to do an AC sweep of this. So we run this and we plot this signal. Okay, so let's look at this signal. So this red one, the solid one, is our gain. Okay, and the first thing that we want to do is we want to look at stability. So in order to be stable, this has to be set up such that the gain at 180 degrees, or the gain at 180 degrees is less than 1, or 0 dB. Or the other way to look at it is when we go down to 0 dB that we have less than 180 degrees of phase shift. So we go down here, we're sitting here at 0 dB, and we look at the phase right here, and you see we have a phase of 128 degrees. So this is less than 180 degrees, so this is going to be stable. So if you look at this, you can kind of see that we go along here, and then here is a corner. And so right around here, you see the phase is starting to change, and it's changing from 0 degrees to about 90 degrees. So this is what you get with a single corner. So with a single corner frequency, we get a 1 plus 1 over j. So when we're past that first corner, we get this. Now, an op amp has multiple corners. So what you see here is that they put most of their corners at a high frequency and put one corner fairly low in order to attain this stability that we've talked about, this feedback stability. So you have a good phase margin and a good gain margin. Okay, so again, to say that again, you see here's one corner that's really low, and then all of the other corners are out here that are fairly high, so that this op amp is always stable. So now let's look at what our 3 dB point is. Okay, so we are going to change this around to magnitude, and we want to find our 3 dB point. So we're going to go to 3 dB, right around there, and we see our 3 dB point is at 1 hertz. So this amplifier has a bandwidth of 1 hertz. Well, you're probably saying, well, that's a pretty dumb amplifier. How many applications have a frequency less than 1 hertz? This is only going to work for DC applications only. How are we going to use an op amp for anything useful? So we need to talk about what happens to the bandwidth when we add in stability. It has to have a low corner, otherwise it can't have a high gain and still be stable. So let's start by looking at our Bode plot. So this is the Bode plot of an op amp. And then lots of times there's other stuff that goes on down here. So this is called my open loop gain, and then this is my corner frequency. So the op amp has one main corner at that lower frequency. So the gain equation is going to be A0 over 1 plus J F over F naught. Okay, so let's go and look up our op amp. Let's look at the data sheet for our op amp. So we grab our data sheet, and let's grab some of these values. So first of all, right here, large signal gain, this is our open loop gain. So we're just going to use the typical value, which is 800 volts per millivolt. So our A0 is equal to 800 times 10 to the third volts per volt, because they had volts per millivolt, so we do it into volts per volt, and this has a gain of 800,000. So a very high gain. That's great. And then also they give us this in terms of gain bandwidth product, which is 0.8 megahertz. So what they're doing is they're telling us the gain times the frequency, so this is gain bandwidth, is equal to 0.8 megahertz. Well, if we want to know what that corner is, F0, we're going to take 0.8 times 10 to the 6th divided by 0.8 times 10 to the 6th, which is my gain. So this is my gain bandwidth divided by my A0 is 1 hertz. Oh, well, that's what we saw in LT Spice. So this is just confirming that that is right, that this point here is 1 hertz. Okay, so now that we have this, now we're going to take this op amp that has a very high gain but very low frequency corner and build it into one of our standard op amp stages. So we're going to start with a non-inverting configuration. So from 240, let's build up our non-inverting configuration. So here is my R1, here is my RF, and here is my V in, and here is my V out. And so now we are going to be analyzing this amplifier configuration with this gain equation right up here. So we're going to take this gain equation and put it into this op amp calculation. So in order to do this, we're going to come in here and we're going to label that V1. We are going to use the approximation that there's no current going into the terminals. So there's 0 current right here, which means that the RF and the R1 are basically in series, and we could just do a voltage divider. So we have that V1 is equal to R1 over R1 plus RF times V out. We also have the gain equation of the op amp, so we also have V in minus V1 times A is equal to our V out. So then we can take this equation and solve it for V1. So V1 equals V in minus V out over A. And we can take that and plug this in to here. Okay, so now we plug those in, and so we get V in minus V out over A is equal to R1 over R1 plus RF times my V out. Okay, so then we can simplify this down and we get V in equals V out times 1 over A plus R1 over R1 plus RF. Now before, if I have an infinite gain, my 1 over A0 right here would go to 0 and I would solve for it. But in this case, we don't have an infinite gain because we're trying to figure out the frequency response. So we are going to take and we are going to solve this. So we want to get the gain. So V out over V in, we're going to call that the gain of my non-inverting stage, which is going to be equal to 1 over A plus R1 over R1 plus RF inverse. So we want to simplify this some more, and so then this is going to be equal to A times R1 plus RF over R1 divided by A plus R1 plus RF over R1. And that is equal to V out over V in, which we're going to call A of our non-inverting stage. Okay, so that's equal to that. So now what we want to do is we want to plug in what is the value of the gain of our op amp. So our gain of our op amp is going to be equal to the open loop gain plus our corner frequency. So then what we're going to do is we're going to take this and plug it in for here and plug it in for there. Okay, so we're going to take this piece here and multiply it times this piece here. And then that whole thing is divided by this plus that same term. Okay, so then what we want to do, and this whole thing is equal to our non-inverting amplifier stage. So in order to simplify this, we're going to multiply the top and bottom times that 1 plus j f over f naught. So then we are left with a0 times r1 plus rf over r1, all divided by a0 plus 1 plus jf over f naught times the r1 plus rf over r1. Okay, and this again is equal to RA. Okay, so then we want to keep simplifying this to get it into a term that we can understand what's going on very well. So we have a0 times r1 plus rf over r1. And then the part on the bottom is a0 plus r1 plus rf over r1 plus jf over f naught times r1 plus rf over r1. Okay, so this term here, is the gain of an ideal non-inverting amplifier. So this could be like 10 or 100. And this is the open loop gain of our op amp, which is like 100,000, or in our case, 800,000. So what really happens is that this one here becomes negligible compared to our A naught. So we can just neglect that term there. Okay, so then we want to put this into our standard equation for a low pass filter. So what we're going to do is we're going to put it into that form. So we're going to have, and that means we want to get it into a form of a 1 plus j f over f1. So the top becomes this. And then the bottom becomes a0 times 1 plus j, and then we're going to have an f over an f naught, and we're going to have this r1 plus rf over r1. Okay, and then we see that these two cancel off, and when we're all done, we get this equal to r1 plus rf over r1 times 1 over 1 plus j f over f1, where our f1 is equal to, whoops, we forgot our a0 in here. Okay, so our F1 is going to be equal to F0A0 divided by R1 plus RF over R1, which is equal to, so our corner frequency was that gain bandwidth product that we had before, divided by the gain of our non-inverting stage. Okay, so let's draw this as a Bode plot to finish up what we have just learned. So our main op amp looks like this. So this is my F0 and this is my frequency. And then what we find out is that we end up getting something that looks like this. So this is my R1 plus RF over R1. And it has a corner that's my gain bandwidth product divided by that my gain of the stage. So what we see here is that we basically take our gain bandwidth product divided by the gain of the stage, and that gives us our increased frequency. So let's look at some numeric numbers here. So let's say that we set R1 plus RF over R1 to be equal to 100. So we really just want a gain of 100, not 800,000. So that means that my F1 is going to be equal to 800 kilohertz divided by my gain of a stage, which is 800. So this is going to go down to 8 kilohertz. So what we see is this would be 100 and this would be 8 kilohertz. Now, if I needed more gain, so we're going to be able to do the same thing that we did before, is we're going to do multiple stages. So I could take my op amps, break them down into multiple stages, just like I did with MOSFET and BJT amplifiers to get, because we get the same gain times bandwidth relationship that we get with op amps as well as we did with our transistors. And so then just to review what we learned, this is our final answer right here for a non-inverting stage, and we use this term right here to find out what that frequency corner is.